All right, so chapter 19 in the Klein textbook immediately jumps into aromatic chemistry. So last term we finished describing what it means to be aromatic. This term we'll start doing functionality or derivatization of aromatic molecules. So let's take a look at some common reactions that you might see students try. And I'll show you one. So let's say we have benzene, and we throw in bromine. Quite often you'll see inexperienced organic chemistry students say, well, there's a pi bond in there. Can't this just add across that pi bond? What do you guys think? No. Why not?
It makes a non-aromatic.
Yeah, right? We started out with an aromatic molecule. Now this is non-aromatic. The reason that this doesn't happen, we know aromatic molecules have a huge amount of stabilization energy. By destroying that stabilization energy, you're actually pushing the reaction in the wrong direction. It wants to revert back to its aromatic state. So this reaction simply does not occur. So we'll cross this out and say does not occur. All right. Alternatively, though, there's a goofy thing that happens. Sorry, I changed pen thickness here so you can see it better. Is if you take bromine and you add in a little bit of iron, what can happen is you can swap on a bromine, right? So if we think about our original aromatic molecule, we originally had a proton coming off this position, and we're swapping it out with the bromine. So now the question is, well, why does that occur? And we'll discuss it in a little bit more detail, but let me first change my pen thicknesses. I don't like the skinny pens. All right, and the reason that this is allowed is we're going from an aromatic molecule to another aromatic molecule. If we look at this, we're not doing an addition reaction, we're just swapping out a proton for a bromine. So this is called electrophilic aromatic substitution, not addition. So let's take a look at the full mechanism and try to understand why iron is so important for this reaction. But before we do that, let's look at the overall mechanism. And again, I'll just write that this is general. However, you can do a lot of different substitutions. You can do one with bromine, you can do one with chlorine, you can do one with the nitro group, you can do one with alkyl groups, acyl groups, you name it. There's a lot of substitutions you can do. But they all follow the same general mechanism where you've got an aromatic compound and you have to have some sort of really, really, really strong electrophile, typically so strong that it has a positive charge. So I'll just write really strong electrophile. And why do you think the electrophile needs to be really, really, really strong? Do you think our nucleophile is very good? Are aromatic rings that nucleophilic? No. And that's the reason we need a strong electrophile, is to compensate for the fact that aromatic molecules aren't very good nucleophiles. They don't want to give up electrons. They're happy with their aromaticity. So this is a weak nucleophile. Okay, so in our first step, what we're going to do is have this pi bond, one of them, attack our electrophile, right? We know those pi bonds can be weakly nucleophilic. However, it's not super happy doing this reaction. And when you do this, oops, you end up with a positive charge on your ring. You end up with a covalent bond to your electrophile. And if you notice, we've destroyed aromaticity. Why do you think this is somewhat allowable, though? What makes this relatively stable? Resonance, right? You can draw a lot of resonance structures where you delocalize the positive charge around the ring. So even though we've broken aromaticity, it is resonance stabilized. And what this is referred to is a sigma complex. Or Some people call this an rhenium ion. Tomato, tomato, I don't really care what you call it. It's just important to remember that it's a resonance stabilized carbocation. All right, and the next step, what you typically have is some sort of weak base. It doesn't need to be very strong because we know our intermediate is really unstable. So in this next step, this base can pluck this proton off, do an E1 type reaction, and reform that double bond. And now we just have our electrophile there. Still getting used to this new pen. I'm sorry if my penmanship is going downhill. And then you end up with your conjugate acid. Does that make sense? Yep.
So Jeff, are you saying, like back in that example of BR2 and with iron, are you saying that E could be BR and then the basis at E?
So I'll show you guys the mechanism for doing the aromatic substitution with halogens next. However, the big thing to remember is this only works if you have a really, really, really strong or really unstable electrophile. It doesn't work with bromine because that's not a very good electrophile. If we think about bromine, it doesn't even have a net dipole. So it's not going to be a very good electrophile for this reaction. So that kind of leads me into my next point. Let's do the halogenation reaction first. And typically there's two different types of halogenations that you'll see. You'll see bromination and you'll see chlorination. You really don't see fluorination that often, at least in our textbook. However, it's becoming a lot more popular, especially in medicinal chemistry. So let's take a look at the most common ones that we'll see. So overall, we're going to start out with an aromatic molecule. And we said with bromine, you add in Br2 and you add in iron. However, the iron, when it's around bromine, will end up forming a complex. What will this be called? Besides FeBr3.
Iron 3 bromide?
Yeah, iron 3 bromide, right? So it forms an iron 3 bromide complex. And that is actually what helps the bromine become a really strong electrophile. And like I said, you can swap off one of the protons for bromine. So let me just make a note. Br2 plus 2 iron atoms can combine to form 2 iron tribromide molecules. All right. Alternatively, you can do this with chlorine. It's less common, simply because chlorine's harder to work with. However, you can do a similar thing where you take chlorine gas, and typically this is done with aluminum trichloride, and you can swap off one of the protons for a chlorine. So same sort of reaction, almost same exact reaction mechanism. So let's do the bromination mechanism first. Yep.
In the reaction equation, how do you go from 2 bromines to 6 bromines?
Oh, I'm forgetting my 3. Thank you. Man, it's a good thing I'm teaching Chem 110 again. I'll be able to remember how to bounce equations. There we go. So the mechanism's pretty straightforward, but the iron tribromide is really doing most of the work in the reaction. And if we think about iron tribromide, there's no lone pairs on the iron, which means it must be trigonal planar, right? Oh, let me change this. So we've got this trigonal planar iron tribromide. What hybridization must it be? sp2, right? So it must be an sp2 hybridized iron, which means it must have a p orbital, right? There's no electrons in this p orbital. It's an empty, vacant p orbital, which means it really, really wants electrons. It's unhappy because it doesn't have an octet right now. Alternatively, what would we call this? A good Lewis acid or a good Lewis base? If it wants electrons? Remember, Lewis bases want to donate electrons, not accept them, right? So in this case, this would be a good Lewis acid. It wants electrons. All right, so then the question is, well, what's going to donate electron density to it? Really, the only thing around that can donate electron density is the elemental bromine. So we've got this elemental bromine floating around. It can donate its electrons to that empty p orbital. So I'll just go ahead and draw one of these lone pairs getting donated in. Doesn't really matter which one. And when you do this, you form an unstable complex that's a Lewis acid-base adduct. So this iron now has a negative charge. The interior bromine, or the bridging bromine, has a positive charge, and then you've got a bromine dangling off the end like that. The bromine with the positive charge is quite unhappy. We know halogens are relatively electronegative. They don't want to carry a positive charge. So it's going to suck a lot of electron density away from the adjacent bromine next door. So there's a strong dipole in that bromine-bromine bond, so much so that essentially it's going to pop off with minimal effort. Okay, at this point, this is our really, really good electrophile. Specifically the bromine, right? The bromine on the far left-hand side has a strong partial positive charge. It's not happy. It wants to essentially be kicked off somehow. So in the next step, we'll have our aromatic molecule, in this case benzene, act as our weak nucleophile. And this weak nucleophile will steal this bromine, give the charge back to the interior bromine, and create our sigma complex. Whoop. So we'll have a bromine here, we'll have a hydrogen here, have a positive charge on one of these carbons. And you can draw all of the resonance structures if you want. However, just for the sake of time, we're not going to worry about it right now. And then alternatively, or not alternatively, the other product that we get is the iron with 4 bromines on it. This is a relatively good base because that iron's not happy having a negative charge. So in the next step, you can show this bond from the iron and bromine reaching out, grabbing a proton, clamp down, when you do this, you restore aromaticity. And you regenerate your catalyst. So the fact that this iron tribromide is recreated at the end of the mechanism means that by its very nature it's catalytic. You don't need very much of this in order to drive the reaction. Does that make sense? The other byproduct that you get out of this is your acid, which in this case is just going to be HBr. That was the bromine from the iron complex plucking off the proton from the aromatic molecule. All right, the chlorination mechanism is just kind of this one more time. So let's briefly do that one. And with chlorination, we have aluminum trichloride, which again, is trigonal planar. And just like with the iron tribromide, you're going to have this empty p orbital sticking up and down from the aluminum. And this time you have elemental chlorine around. That's going to be your weak Lewis base. And it's going to donate its electrons to that vacant p orbital sticking up and down through aluminum. And just like before, you form this relatively unstable complex. I'm not going to show stereochemistry for this since it doesn't really matter. Where just like before, there's going to be a strong net dipole. Actually, let me change the colors. Where that chlorine on the far left-hand side is incredibly electrophilic. And then in your next step, your aromatic molecule is going to steal one of those chlorines. So now we have a chlorine here, positive charge, proton, 2 pi bonds. We still have this aluminum complex floating around. We want to restore aromaticity. So just like before, we're going to take one of these chlorines and its electrons, grab a proton on the sigma complex, clamp down, and try to restore aromaticity. So now we regenerate our aluminum trichloride, and our conjugate acid in this case is going to be HCl. Does that make sense? If you think back to last chapter, the only way we knew of for functionalizing aromatic compounds was at the benzylic position, right? So we could do benzylic halogenation. So for example, if we had toluene, we could turn that terminal carbon into a halogenated hydrocarbon. How did we do that? What reagent do we need? NBS, right? If we wanted to change a benzylic carbon into a carboxylic acid, what do we need? We could use potassium permanganate, or we could use chromic acid. The nice thing with this one is now we don't have to worry about benzylic chemistry. We can actually functionalize the aromatic ring itself. If you think about this, what's something nifty we could do with, let's say, bromobenzene in order to turn it into a super strong nucleophile? Grignard reagent, right? So if we throw in magnesium, the magnesium will insert in between the carbon-bromine bond, and now we can turn an aromatic molecule into a Grignard reagent. So that's a really powerful tool that's quite common in organic chemistry. Does that make sense? In fact, your second lab, that 4-week lab, you're going to be doing a lot of chemistry just like this, so electrophilic aromatic substitution chemistry. It's still a common reaction that's done today. That's one reason I like teaching this as opposed to some of the other reactions. I think I've told you this throughout the year. A lot of the reactions we learn are these old school reactions from the 1950s that no one does anymore. These ones are still relatively common. All right, there's one last reaction I want to show you guys before we call it quits. And this is sulfonation. And this follows the same reaction mechanism, but with different reagents. Again, you need an aromatic molecule to be a weak nucleophile. This time we're going to take sulfuric acid, H2SO4. However, it needs to be fuming sulfuric. And some people will ask, what is fuming sulfuric acid? I remember once in grad school, one of the students I was working with thought it just meant really hot sulfuric acid, like it's fuming. Not so. Fuming sulfuric acid is very unique and different from regular sulfuric acid. Fuming sulfuric acid has sulfur trioxide added. So let's make a note. And if you think about sulfur trioxide, it's a weird molecule. If you remember back to Gen Chem, sulfur quite often violates the octet quote-unquote rule, and that's because it's further down the periodic table. It's got other stuff going on that we don't typically see in most organic chemistry. But if you think about the resonance structures for this, the sulfur-oxygen bonds aren't really a true double bond. In fact, They're in between a double and a single bond. So the sulfur has a very strong partial positive charge. That means that this sulfur is a good electrophile. And that's why fuming sulfuric acid is so essential for this reaction, is we need a really good electrophile for the substitution to occur. The only way for a good electrophile to be around is to actually add in that sulfur trioxide. All right, so when you go ahead and do this reaction, we're going to swap out one of our aromatic protons for a new sulfur-containing group. Typically, these groups are used as blocking groups, and we'll talk more about what that means later. But the nice thing with this reaction is it's reversible. You can actually put it on and then take it right back off in the next step if you want. So it can essentially be a placeholder to prevent unwanted side reactions from occurring. So let's take a look at the mechanism. All right, just like before, we started out with this aromatic ring system we know is a weak nucleophile. We know it needs to react with our strong electrophile, so I'll show our sulfur trioxide in the first step. It's going to attack the sulfur trioxide and then kick up electrons onto one of those oxygens. We're going to make our sigma complex. Oh. Sorry, this pen is weird. I'm still getting used to writing. Feels like I'm writing with a crayon. And then in the next step, your sulfuric acid, because it's a strong acid, typically exists mostly as a conjugate base in solution. So this can actually, believe it or not, act as a base. It's a really crummy base, but it works because this aromatic molecule wants to have its aromaticity back. So it'll steal a proton. Actually, let me slide this down a bit more. And then in your next step, you've got this sulfuric acid floating around as your solvent. And because it's such a strong acid, it can actually protonate that oxygen in order to make a sulfonic acid. The cool thing with this is if you want to go back to square one, back to your aromatic compound, all you need to do is run this reaction in dilute sulfuric acid. What does it mean to be dilute again, just to clarify? Just means having a lot of water around, right? So dilute just means lots of water around and some sulfuric acid. It will actually remove that sulfonic acid group. And like I said, this can act as a removable blocking group. Does that make sense? So chemists play these games a lot. If you remember back to last term, we do things like protecting certain areas of our molecule or blocking certain areas of our molecule to avoid unwanted side reactions. This one's really nice because it's easily removed using standard conditions that can be done in most lab settings. Does that make sense? All right, I think we have time for one more. Probably won't get into the full mechanism, but I do like showing this one. This is nitration. And again, it's really similar, the overall mechanism. Where we can have something like benzene. We treat this with nitric acid, which is HNO3, and then sulfuric acid, H2SO4. And when you do this, you can install a nitro group onto an aromatic compound. And nitro groups are pretty interesting because there's Witter ionic. What does Witter ionic mean? Going back to first term. Means it has both a positive and negative charge, right? So if you think about it, the nitrogen has a positive charge, the oxygen has a negative charge, and there's resonance, right? So each oxygen can share partial negative charge. So it is a unique compound. And let's take a look at why this is a common or famous reaction. And I'll show you the most standard example. What's this called? Toluene. What they found in the 1800s was you could take toluene, which is found just in petroleum refining. You can add in nitric acid in excess, along with sulfuric acid. And you can actually add in multiple nitro groups. So you can add in a nitro group right there. What position is that? It's ortho. You also get one para. And then you also get another one ortho. Does anybody remember what this compound is called? TNT, right? It's the molecule that changed the world. Nitro groups are really interesting. They're strong electron withdrawing groups. However, if you get too many nitrogens or nitro groups on an organic compound, they tend to be violently explosive. In fact, what chemists do is they measure the carbon to nitrogen ratio in organic compounds. And when that ratio gets too low, chemists immediately squirm a little and they say, I don't want to work with it. Simply because these want to liberate nitrogen gas and they explode violently. More and more people have switched away from things like TNT, which are shock sensitive, to more safe explosives. So if you've worked in the military, you're probably familiar with C4 and HMX. Those are really, really rugged. You can hit them with a hammer. You can light them on fire. They won't go off unless they've got some other charge to facilitate them going off. Does that make sense? Even then, though, HMX and C4 have a lot of nitro groups installed on them. They aren't aromatic, but they do have a lot of nitro groups, which makes them explosive. All right, I think what I'll do is stop there today, let you guys get out of here a few minutes early, and then tomorrow when we come in, we'll start working on the mechanism for nitration. I do want you guys to try to get started on the pod right away, though, and try to shake off the cobwebs and remember some of the reactions from last term. So if you do want to stick around, you can get started on that.